Okay, excuse me. In this video, we're going to continue on from the motion analysis that I showed and move into the structural analysis. This, in the last video, we showed how you can connect things together so that you can analyze a system to the external loads that make more sense, right? It, Applying it to this example here, I have this inner arm that is the component where I don't have a good design for, right? The brackets, they might end up being pretty much like this, right? Like it's not a terrible design. You might make it a little bit better, but there's not a, a lot of changes I might make to this. We might put the motor someplace different. We might use a belt system, um, but uh, it gave that concept of what what forces and torques are needed to lift this arm up. And we could do some further studies. I was thinking in between these videos that you could do a study on, how much if we gave this arm a target, right? We don't want this arm hanging out in the, I'll call it the pickup position. We want it in the stowed position. And when it's picking up a coral, we don't want it out there for very long because the longer it's out beyond the profile of the robot, the more likely it is to get hit. So we could say, hey, we only want this thing out there for a maximum of 4 or 5 seconds, right? So we could set up this motion simulation to extend the arm and then bring it back within 5 seconds or 4 seconds. And given the weight of this, we put that as a mass on the end of this, we can see how much acceleration is being driven. And that would be a target that we would put on the claw, right? The claw needs to have a uh, uh, it needs to hold that coral in with this, amount of acceleration applied to it, which would be a force, right? So maybe it's 10 pounds, I don't know. Um, but that's a target that motion would be um, very good at determining, right? Um, but today we're gonna look at structure, and what I've done is pretty much already set this up because I didn't want to, it takes a little bit to set it up, and I don't think the purpose of this video is to show you how to use this software. It's to show you that these types of software exist. And if you choose to use it, say this competition year, I can go through with someone to have them use it. So what I'm trying to do today is to just show you generally how it's set up and what are the results or what do you get out of it. So we in motion had already set up some joints and the general structure and or the general connectivity of everything. In structure, the motor isn't really used and that sort of thing. So we basically lock it, right? We've I've locked the motor because we're going to analyze this arm in this position. Um, you can analyze it in a couple of positions, doing separate analysis, but right now I'm just looking at the arm in the extended position. This is where I feel most of the loading could occur. And most of the loading in my mind is this arm being hit by another robot, right? When you're trying to get this coral, um, you're the arm is susceptible to another robot coming in and smacking it. And so one of the uh, loadings I developed was that another robot comes in and hits this straight on. And so I think I have a load here of, let's see, 50 pounds, 222 newtons. So I believe that's about 50 pounds force. Um, I have a separate loading here, which is, again, 50 pounds. And then I have a third force, which is the pickup force. And that's basically, that's not really a collision force, but that's, in my mind, a force that this arm comes down and how much force is going to be generated possibly when you pick this up. And I put it as 25 pounds basically. Um, and people can argue about this, right? Uh, Obviously, a robot coming in could be much larger force for collision. Um, but how large do you want this arm to be? Um, and how much force do you need to sustain is a design uh, decision that you as an engineer make. Um, and so I've made this decision, and if it changes, we can go back and redo the analysis. Um, so that's the loading that's applied to this. Um, so that's kind of one of the the conditions for a structural analysis, right? You need the parts, you need the loading, you need the supports, and basically the supports are where you're going to hold this. And in the motion analysis, I I basically grounded these parts here. Um, in structural, you use boundary conditions. Motion, while all these analysis are in the same program, um, motion analysis, like a rigid body dynamics type solution set, it's a totally different analysis solution, and some of the constructs for that solution set are different. And the structural is, a deformable body, and the boundary conditions are the way you hold parts. And so I've applied two supports, and they're just down here at the bottom of the rail. Um, the the coral itself doesn't even, I'm not using it in this analysis, and I'm just going to hide it. And the bumper is non-structural for this analysis, and I'm going to hide that. Um, Really, these wheels are kind of just transmitting the locked motor, so um, they're not really, the coupling that we had set up actually keeps that locked in place. So they're not really necessary either, um, but I'll just keep them visually there. Um, so now I have the parts set up. I've, in the motion analysis previously set the materials, so I'm going to keep those the same. And I'm going to look at setting up the main element I want to look at, and that's this inner arm. So let's turn everything off and look at the arm. Okay. And one of the things I did with this arm is I partitioned it, is the term in the software. And it is, I cut these radiuses. So they exist um, uh, in the structure, but these are non-design. Uh, uh, they don't they won't participate in the optimization I'm going to do. So they will stay exactly the same, and that's typically, well, one, when you're doing an optimization wherever the part's being held, you want to keep that out of the optimization. It's just you get weird results when you allow the optimization to um, eat away or change the structure where forces are directly being applied to it. So I partition this out, and these blue pieces will remain as they are. But the brown part of this structure will be allowed to change, and basically, or specifically, the simulation will allow this to be parts of this volume to be removed. And basically, we're going to do a topology optimization where the analysis removes parts of this volume that don't participate in the support of the loading. So I've set up 3 loading conditions. All those conditions will be analyzed, and volumes that don't add to the structure of these, what's holding this together, could be removed. And so that's kind of what I've done to this part. I have added shape controls. So one is I've designated that this is the part I'm going to look at. I've designated this plane of action, and this plane of action is really like when we would do this for cast parts. This is in a casting, you have a top and a bottom mold typically, and this is where you're going to separate the mold. And although this isn't going to be a cast part, I wanted to set up a direction of orientation for that, and that's what I defined this as, and it's basically through the center of this hinge here. And then the other thing I did is I created a symmetry. So I said that the part should be symmetric left to right. So this side of the part should be symmetric to this, and this is the symmetry plane. So that's the other definition I did to this. And then uh, of course, and I set this as I think a plastic ABS type material because I thought this could be 3D printed. And right off the top of my head, I don't know what uh, the structural properties of 3D printed materials can be. I'll probably ask some people when we get back into the season. Um, but right now, I just assumed it's kind of like, I think, an ABS type plastic. Um, so that's that. Um, and then I ran this solution. Um, and I did an initial analysis where I just looked at the stress. I'm not sure if I have any. No, I don't have. These are like pre-analysis, but I don't have the analysis on me um, to look at where the stresses are going through this system, how it's working, and such like that. Um, and then I did an optimization. Um, I did a couple of optimizations, um, and one optimization gave me uh, this result. So, and basically what I was saying is the optimization determines where it basically assigns everything in this volume. It divvies it up into cubes, this volume into cubes. And each smaller cube has it's called a density function, but I'll call it a participation function. And basically each cube is defined a participation function. So if you have high participation, you uh, you a lot of load is going through that volume. If you have a low participation, then not a lot of force is. So in a sense, you're kind of taking away the structure in those low participation areas. But it's a continuum. You know, some parts have 90% participation, some parts have 10% participation or 30% participation. But you have to kind of cut it off, right? So um, if we say look at, I think I can look at this analysis here. Um, let us see. Yeah, you can see that as I'm going to make everything, turn everything off. Okay, so as I move this slider bar up, why is this? No, I didn't turn this on. As I move this slider bar back and forth, I'm basically going from 0% participation, show everything that is 90% participation or more, which I'm just making up a number, but versus show everything that's 10% or more, right? So we can see that um, here, as an example, everything that is shows like 90% participation um, shows up as brown, and those that are have 10% or less is visually removed. it's still in the analysis, but it's visually removed because this analysis is just here to show you where the structure is most effective. And it's now part of the person's job is to determine where you're going to place this. How much are you going to allow to for the structure that you're going to use, uh, where are you going to set this cutoff? And so I think I set it around someplace around here. And I generated a smooth surface from this. This is actually very, let me take off smooth results. You can see that when I said squares, it's actually triangles. And you can see the triangles here, and it's very rough, and that's part of the um, issue is this is, in a sense, a stress analysis, and when you have rough surfaces, you have stress concentrations, and that's part of the uh, internals of the software dealing with this is how do you smooth out the stress? How do you get rid of stress concentrations? Because you don't want stress concentrations to drive your answer. And they do it through a series of averaging. You average uh, stresses from elements in the neighborhood of the element you're looking at. And then visually, they just smooth it so that it's a little more um, easy to see. Um, and then um, I did want to show this result. This is a wrong result. And what had happened is I had run this. This is the first time I run it. And um, I had forgotten to check the contacts. So in part of making this software easy, they set up some contacts for you. And since the lower arm and the gears, um, or the outer arm and the gears that are attached were here, it put in some contacts. And when I looked at these results, I'm like, why is this structure here? And that's the job of you as an engineer is like, does this make sense, right? Because um, why would it put structure here? And so then after some investigation, I could see that, yeah, there shouldn't be anything here. And I went into contacts, and there was this contact here that was driving material. So I removed those, and you get a much more reasonable answer, right? Um, where we're just using this to drive a design, we're not using this as validation. Um, this as when you think of the loading and you think of the way this part is set up, this is a much more reasonable design. You would understand that this should be an X type structure. Whether the center of the X should be here or down here is a variable, right? But that makes more sense. So after this, I smooth this, and so I'm going to turn this off. And oh, and also, let me turn it back on. These partitioned parts that I took out, as you can see, they stayed the same, right? They're not in the structural analysis. Um, One of the things I did when I did this is I kind of carved out a little bit more. Um, since I'm using this to kind of guide what I would design, I probably wouldn't do that, right? You look at the results and you see that the results are right along the side here. So I would probably keep this, from whatever I'm putting in here. If I'm putting in a bolt, um, um, I'm not locking this down because this needs to be a hinge, but putting a bearing or whatever, I would try and keep this line of action, right? As long as I have the package space to put the bolt and the bearing in, um, I would like to keep this material, right? You can see that it probably wants to keep this here. So that's kind of the intent of this analysis, is to guide your design, right? You can see here, as we go through here, right, it doesn't really say, it says I don't need this material as much, right? So that's kind of another thing. And luckily, it also says, right, we don't need material in here. So this arm, this top arm or the outer arm can be the way it can remain the way it is, right? It doesn't impinge on the structure. Um, so I'm going to turn this off. And what I did is I fit, they have a set of polynerbs, they call it. And basically it smooths the part out a bit, and then you can export it. So I generated the polynerbs, and I will set this um, geometry and bring it into uh, uh, Inventor, and come up with a concept from that. Probably, thinking about what you would like to do, you could do a bent piece of aluminum, you know. Um, Possibly you could do of course, 3D printed, possibly. But again, you want to, you know, base your design off this, right? Uh, so that's where we are with that. And I'm probably going to leave that here. I don't think I'm going to go any further with this. Um, if we want to have kids generate actual parts, um, we'll see as we get along in the season for practice. Thanks very much. I hope it was interesting for you, and I'll see you soon.